Hello, welcome to my YouTube channel today. Today's video is kind of a follow-up from yesterday. I want to go through the pinout of my bus controller. So I've got it running right now. We'll just see if it stays running while I go through this, see how stable it is. This is as much for my notes as for anybody that is wanting to cut and design a similar item. So it's always hard to start or know where to start on these descriptions, but I'm going to start with kind of the counter. So for the counter for the bus controller, I've got an LS161, and starting on pin 1, I've got this connected through an LS04 to the data enable coming off the V30. So data enable, LS04, inverts it, and goes to pin 1. That's the clear pin. The next pin's the clock, and I've got this connected to the same clock as the processor, so it's synchronized. I have been working a little bit trying to do some, like a 16 megahertz clock to kind of speed things up. Have some success, but so far I've been most successful keeping it synchronized. So this is connected, synchronized to the click pin on the processor. The inputs on the counter are not connected. And then this would be pin 7 is connected to the ready off the ISA bus. So this goes up to the ISA bus. And it's got a pull-up resistor on it. I think it's 5.1K or so. And that allows the counter to count as long as it's being pulled up. So any device that needs to be not ready will pull this down and it'll stop the counter. The ground's connected to pin 8 here. Then pin 9's the load pin, and it's connected high. Low is to load, high is not. 10 is another enable pin. It's got to be high, but I've got it connected to the output on one of the pins on the ROM. I've got it connected to the D6, actually, and I use that as a stop signal for the counter. The counter outputs, so they kind of cross each other here. They're not lined up with the ROM, but counter 0 through 3 are connected to the inputs on the ROM, A0 through A3. And so that allows this to count up to 16 places, starting at 0. The ripple counter out is not connected, and then the power is connected to the last pin there. On the ROM, so overall, any of the address pins that are not being used are connected to ground. So if I miss any pins, they're connected to ground. We got our power connected in the top corner, our ground connected in the bottom corner. And then as discussed, A0 through 3 are the inputs from the counter. A4 is connected to A0 coming off of a latch. Now, coming off the processor to the latch, A0 does not go to the ISA bus, it goes to the bus controller. The next one's bank high enable, same thing, it comes off of a latch, it does not go to the ISA bus. The next pin is A6 is connected to DTR. So this is connected directly to the direction pin out of the processor. Now, probably should have said this in the beginning, but this is connected in minimum mode. If I was running this in maximum mode, it'd be connected the same way. I would just be coming off of an 8288. We're just saving a chip, and then, as I've talked in my other videos, getting sidetracked here, but I want the hold and hold acknowledge that minimum mode provides. I don't want the request and grant pin. It doesn't work well with the DMA controller. So A6 is connected to the direction right off of the processor. And then A7 is connected to chip 16-bit select. So this is coming from the ISA bus, the memory chip select 16 and the IO chip select 16. And that's decoded through an LS125 using the IO mem select. So if it's selecting IO, it's going to give you the IO feed. If it's mem, it's going to give you the memory feed on if it's a chip select, and this is active low. And then the next two pins are connected to ground, the address pins here. I think they're like 12 and 15 or something. But the next one that's important is address 8, and that's connected to the interrupt acknowledge. So this is the last one that's connected for decoding. So interrupt acknowledge, the chip select 16, direction, bank high enable, address A0, and then 4 pins or 4 address pins for counting, so 16 places. Now on the outputs, I've got D0 is what I use to enable the data transceiver. So for the 16-bit side or the upper D8 through 15 and the lower D0 through D7. Now, so the output of this goes to an LS139, and I tied, make sure I've got the right side of this here. I tied the inputs. You got two inputs, 0 and 1. I think they're listed as like A0 and A1. One is tied low, so we're just only decoding the one wire coming in. And I do have the data to enable come into this as well, so that can actually, it works as a shutoff for this. So if this is low, I call that normal operation, so that's straight 16 across, 16 back. And if it's high, I call that not normal operation, and that would be an 8-bit read or write. Now don't get sidetracked again. Not to get confused with, like, if you're doing a 16-bit operation, but you're only doing like the high side or the low side, you're still going to be in normal mode because it's just a direct across transfer versus a not direct across, which would be the latch and the transceiver that goes from the high side to the low side. So that's what D0 is connected to. D1 is connected to, it goes out to the LSO4, and it goes to the latch enable on, or the latch pin on the latch. So this is for a 8-bit to 16-bit read is pretty much all this is for. So the first byte is read, the 8 bits are read into the latch, and it's latched. And then address 0 is incremented to 1, so it starts at address 0, 0, and it reads that byte, latches it, and then address 0 is incremented by 1, and then we read again, and that comes through the transceiver to data 0 through, or data 8 through 15. So D1 is for latching that value. D3 is the read-write pin. Now, this is active low, high it's inactive, and it's both read and write, which may get confusing. What I do is I come over here to the LS139 again, and this is connected to the input 1, and the direction, the DTR wire, which is also connected here, but the DTR wire is connected to the input 0. So that selects is it a read or a write, and data 3 here is basically is it active. And then you can see this is read write, and it goes up here to the support board, and then there's a LS, I think it's a 257, that decodes this and the IO mem pin to generate whether it's a memory read-write or a IO read-write. And then D4 is address 0, and this goes to the ISA bus. So that way we can manipulate address 0 independent of the processor and independent of the latches. B5 is your bank high enable, so same thing as address 0. So bank high enable goes to the ISA bus, and it's independent of the processor and the latches. Now, let's see, so the next one is, this is address latch. So D5 is, I might have got my counting off there, but D5 is address latch, and it goes to an LSO4, and then from the LSO4 it goes to the ISA bus, and that creates the address latch on the ISA bus. So one thing I should mention is everything in here is active low, regardless of what it should be. So that's why the address latch has to go through an LSO4, because it's actually active high. I just did that just to try to keep things less confusing when I was coding it out. And then D6 is your stop bit, and I actually tried to remove this recently, and I found that by having it, it ran a little smoother. Because originally the stop bit I just had tied to the final D7, which is the ready signal. So the ready signal drops low, goes through an LSO4, and goes to the processor, which is high, and tells the processor that the bus controller is done. So you would think that you could just tie these together. Once this drops to low, it stops the counter. But I think it came down to reading. It was better to have the read signal still active when you give a ready signal for at least a click, and then send a stop bit out to stop the counter. So I was able to cram all the signals into one ROM. But of course it requires a little bit of decoding externally because of that. Let's see, so what else we have here? So the rest of the address lines are connected low. The chip enable is connected low, but the output is actually connected to the hold acknowledge. So if the bus gets held, it will cause the outputs to float. Now, obviously the ones that go through an LSO4, the output on that doesn't float. So I need to go through and make sure that anything that's touched in the ISA bus when hold acknowledge is active is floating free. And so right now, I think the address latch is the only one that's not allowed to float free. So that's the counter and the ROM. In the process, I talked about the LS139 and the LS125, which these are just connected. It's just got the inputs from the backside of the ISA bus there for that chip select 16. So let me go through the processor. So I'm going to start with pin 1, which is connected to the ground, and then the next few pins, so it's address data 14 through address data 0 going this way, and they're connected out to the latches so we can get the address, and then the data is connected to the transceivers. So it's the same wire, but connected to the latches, the inputs on the latches, and then the inputs on the transceivers. And that's your address bus and your data bus. I'm going to go over to this side real quick because you've got data or address data 15 here, and you can see that connects to this transceiver here. This, if you saw my last video, is actually 2 chips stacked on top of each other, soldered together. So this provides the normal transceiver that goes data 8 through 15 over to the ISA bus, but it also goes to the 8-bit side of the ISA bus for 8-bit transfers. You've got address 16 through 19 and bank high enable, and they're just out to latches. That's the only thing they're connected to. The min max is connected high, and then the I want to say it's the read pin's not connected and the write pin's not connected, but your hold, and I've got a pull down resistor, and your hold acknowledge are connected to the board, which actually connected to the DMA controller. And then you've got your IO mem, which is connected to an LS04 inverted, and it goes to the support board here. And the reason why that's inverted, the IO mem, is because an 8088 memory is low, but on an 8086 memory or IO is low. So I had to invert it. And then the IO mem also goes over here to the LS125 to differentiate between whether it's a memory read or a IO read or write for the 16-bit chip select. And then try to do this all for memory. The DTR, it's connected to the input on the ROM and on the LS139, but it's also used on the 3 transceivers, the direction pin on those. And that makes it so we don't have to provide a direction pin off of the ROM. The data enable, it's connected to the ROM and it's connected to the LS139. Let's see here. See if I lost track of something. So, address latch is connected to the latch on the addresses, the latches. We've got 3 latches for the address, and that's the only thing that one's connected to. Kind of skipped the hold acknowledge for what it's also connected to the address latch enable. So it's pin 1 on the LS 573s, and that, so when it gets held, it makes those float as well. Interrupt acknowledge, it goes up here, which connects to the interrupt controller, and then there's a test pin, which is connected low. It's connected high. I guess I've never used it. There's a command, I guess, test, and if this is connected high, it'll stop operations. Then you're ready, which is connected to the LS04 back to the ROM for the ready signal, and then your reset, which right now is coming off the reset of a 8284, the clock generator. And actually we can just push the reset button there. Oh, the screen's not on the camera, I just hit the reset button. So the only ones I missed was you've got the ground in the bottom corner there, and then you've got your clock input, the interrupt request, and your non-maskable interrupt. The non-maskable interrupt, it all connects back to the support board, and it's actually your channel check off of your ISA bus, goes through some logic, and it has to be enabled, and it'll cause a non-maskable interrupt. I'm going to try to turn this, and maybe I should have done it sooner. Let's see if we can get a little bit zoomed in here. So on the back side of the ISA, this bus here, the only thing that's connected is the read-write, the memory read-write, the IO read-write, and the ground, the power, and then, as I talk, the chip select for the 16-bit for the IO and the mem. Other than that, there's nothing on the back to really talk about. If you just pull up a ISA diagram, you can see that. This could be this could be hard to see, but I do want to talk about this. So the ISA bus, the way this is connected, you've got D7 through D0 connected, and it goes to the transceivers. Then you've got the ready signal, which goes down here to the counter. And then address, I did not, AEN's not connected to anything. That's part of the DMA controller. but address 19 through address 1 are connected, or is connected to the latches. Address 0 is connected to the output D3 for the ROM. That's the one I think I confused earlier when I was talking through the ROM. And then down to the 16-bit side, you got bank high enable, which connects to D4 on the ROM. And then you've got some latchable addresses. I'm trying to remember how many there are right off the top of my head. Well, being an 8086, there's only 3 connected, 17, 18, and 19. The rest are connected to ground. I think it goes up to address 23. So there's 4 that are connected to ground right here. The one thing I did was I just ran some wires from address, the latched address 17, 18, and 19, just to simplify it. If I was doing a 286, I might take a different approach, but where I'm not, I just want to leave this latched. The next pins I've got are their read and write for memory. And from what I've read, this is where it gets a little like in the gray area. But the memory read write on the 8-bit side is supposedly only active when it's a below 1 megabyte. And then this memory read write is active all the time is what it says. Not just above 1 megabyte, but all the time. So, being that this system only has 1 megabyte capability, I just tied the memory read write together. If I made a 286, that's going to have to be designed differently. And then you've got your data 8 through 15 connected, which come over here to the transceiver. Now, while I'm thinking about it, one of the things I've been kind of concerned about or wondering about is this chip select 16 comes over here and it's not latched or anything, and I'm wondering how long is that active? Because let's just say it pulses or something. Well, the bus controller will run in 8-bit mode. So let's just say the way this is working, it could start in 16-bit mode, go like two clicks, and run in 8-bit mode after that if this changes to high. And that could get... It's almost like there's no way to detect it. Now, what I did was, if you watched my previous video, I removed all the microcode from the ROM for the 16-bit reads, and I put an LED connected to this line and I turned it on, and it won't boot because it's saying I'm 16-bit, the VGA card is. And that LED just went low and nothing happened. I've also tried to latch it to the regular latches so that when the ALE off the processor latches, to try to grab it, that did not work. It was almost like it was a little too soon. The screen didn't initialize correctly. It was just all weird. So I got a separate latch, connected it up. As you can see, there's no room on this board to play with, so I had to put it on a sideboard. And I used the ALE off the bus controller to latch it. So about a click or two in on the microcode, I latched it. And it made no functional different from what we're currently running. So my thought right now and everything I can see, this stays active low from the card through the entire bus cycle until it's complete. And I'm going to go with that for now on this design. So that is something that's kind of come up. So that's kind of the board in a nutshell. I know I didn't hit the transceivers too hard, but they're pretty straightforward. There's the enable line, and there's not normal and normal, which come off of the LS139, which is activated by data 0 off the ROM. Other than that, they're connected from the processor to the, I want to say it's the A side of the LS245, and then the B side is connected to either the 8-bit A0 through 7 or D 8 through 15 on either one. And the only thing that selects the difference is that normal or not normal operations. And then the low transceiver for the D0 through D7 is it's the same thing. The normal one's here, the not normal's the latch. So I'm gonna take a minute. We're getting a little long in the video, but I'm going to take a minute and go over the microcode. Let's see if we can do this without shaking everything up too much. Now, I've had where I've filmed screens in the past like this, and I've actually gotten comments where it's like, hey, get some data or some screen capture software and all that. Well, my channel's not monetized, so it's not very cost effective. All right, so what I have here is, this is not exactly the code I'm running. Here's the code I'm running. Let me move this over. If you can read that, you can see, let's see if I got this. Let's get this a little closer. That's better. So 0 through FFF, you see is 3E. That's the microcode, and the reason being is, if you recall, knowledge is in address 8, and everything above that is tied low. So basically 0 through FFF is an interrupt acknowledge cycle. I don't care what the other pins are at all. And what 3E does is it puts the transceiver in normal mode, and it sends out a stop bit, and it sends out a ready bit. And so it just doesn't really care where we're at as far as like any other signals. I'm sure it's the same signals every time, but this is just kind of a blanket catch-all. If it's an interrupt acknowledge, bam, it's done. So really we're starting here at 100, and this is in hex, of course. And you can see it just goes across, and this would be counting up with the counter, and these are the outputs. And when it gets here where it sees FFF, well, this 2-6 is the stop. The 2E is a stop. The 3-6 is a stop. This line's blank because this would be address 0 is high, and bank high is high. Bank kind of a, anyway. It's not a true cycle. Same thing with 170 here. It's not a true cycle. But you get down here into 180. You've got some not cycles in here. These could actually be cycles, though, if you were to swap out the processor with an 8088. So down here, I've done it before when I was playing around with it. And you can put, because you would get bank high is high and address 0 is high with an 8088. Bank high being high would be kind of like a default. It's not what it actually puts out. It's not even a bank. There's not even a bank high on an 8088. So I would just set it by default to be high. And that's where that code goes. So we're way off subject here. All right. So I kind of created this as kind of a map to help visualize what we're trying to do. And you've got your D0 through D7, and it's got what they are. Your count, A0, bank high, direction, and your 16-bit. And then interrupt acknowledge isn't listed, but it's because I just know that interrupt acknowledge overrides everything. And you can see, so this would be 8-bit to 16-bit read. And you can see it starts with a latch, bank address 0 is low, and it's in not normal mode. and then I put a space in here. I've taken this space out before and it gets real glitchy. Been doing a lot of fine tuning, but for now that space is still in there. Line 3, we're going to go read write, and we're going to enable the latch on the data, and then it's going to hold it for 4 counts. Keep in mind this is running at 8 megahertz, so this gives it some time to process. Now, as I said, this is, so this is 80. Let me go back here. So if you come to line 80, you can see F1 is the read. I've got 1 of them. Right here in the template, I've got 4. So this is just a template. And by taking these out, it speeds it up. So also you add wait states. You add wait states right here. And then the latch stops. I want to stop the latch before the read stops. And then the read stops, and then address 0 goes to 1. Keep in mind, this is still an 8-bit to 16-bit read. Bank high enable is never used in 8-bit mode. It's always just 1. Anyway, so it sends out another ALE pulse. So the ISA bus just sees it as a read and a read. It doesn't see it as what it really is, which is a double read. But anyway, so that this line's blank, there's a space, and then the read is enabled. You don't latch it because you don't latch this one. And then this is where you give the ready signal, and then 1 count, and you do the stop signal and shut off the read-write pin. And compared to a 16-bit read, which now I haven't updated this side over here yet, but I've been putting FF as the first value, because when the bus controller's not in an inactive, in reset mode, it should be at address 0, and I don't want any random signals being given out. So this doesn't show it, but let's go back here. You can see the whole first row here all the way down is Fs. So I did add that in there. Yeah, so the 16-bit, it starts out with an address pulse. Both bank high and address 0 are low. It's normal operations. We've got a space, and then the read-write is active, and then we go to a ready is ready, and then a stop bit. And that's the difference between an 8-bit read and a 16-bit read. I'm not going to go through all of these, but this would be an 8-bit even side, an 8-bit odd side. So this is reading from the 8-bit bus only, but into the odd side of the processor. As you can see, it's like the transceiver goes to normal mode, but it's half as much as the 16-bit read, or sorry, the 8 to 16-bit read. You come over here to 16-bit operations, and it's very much the same as the 8-bit single operations. And the only difference is you are toggling that bank high enable pin, where in the 8-bit operations you're not. Write is basically like the opposite, but you can see the read-write pin is the same pin, read-write. You don't ever use the latch in when you write, because you're just displaying it out the processor, and then it's just writing it to each appropriate side. So 16-bit. So if you look across these, the only one that's a double is write 16 to 8 and read 8 to 16. Is the only ones that are a double operation. Everything else is actually just single operations with just a few minor differences. And then you come down here, and this is interrupt acknowledge. As you can see, it just doesn't matter. 8088, this is if you wanted to swap in 8088 in there. If you do that, you got to put your bank high enable high, and then the chip select 16. I don't even know if I want to get into that. Because you could go with an 8088 to a 16-bit bus. But it kind of get to be like, why? I don't know if I will actually build my card to be interchangeable 8088 or 8086. So anyway, kind of got long-winded, but that's the big thing is I know that when I was reviewing the pinout, the ones that were closest were the clock and the ROM, but that's what's most important. The rest, I guess I've put enough 8088s together that I just know where the rest of the pins go. So this is what makes the magic happen with the 16-bit ISA bus to the 8086. So anyway, if you made it this far through the video, thanks for checking it out today.